So today I'm going to talk about modeling search term revenue. This is a problem I've worked on and off at System 1. So I'm a data scientist at System 1. It's an ad tech company located in Venice, so not too far. So here's what we're going to talk about. Start with the data science problem we're trying to solve. Then we're going to move on to techniques for handling categorical variables in general. Then I'll talk about the first solution that I had for this problem that we're trying to solve, which involved a mixed effects model. Then moving into embedding layers and neural networks and why this was a cool solution for the problem we were doing, and maybe some conclusions from that. Cool. So here's the background. On System 1, we bid on tens of millions of keywords across multiple pay-per-click model or marketplaces. These keywords have been organized in sort of an ad hoc fashion. They're grouped into different categories. Some are semantic based, so like you can have like cars or health or finance, those kind of categories. And then some are based on like how much a keyword's worth. So we have some categories are like these are high value keywords and these are low value keywords. So it gets a little tricky. Sometimes there's 100,000 keywords in a category. Sometimes there's a lot fewer. And then the sort of behavior of these keywords is quite different. Some keywords can spend up to $100 a day, sometimes $1,000. Others only spend a few cents each month or each week. These keywords do exhibit predictable seasonality, but then there's a whole swath of keywords that only get traffic around specific holidays. And then there's a lot of keywords that just kind of look like a random walk. So it's sort of a tough problem to solve. So this is just an idea of what it looks like in terms of number of keywords and revenue percentage. So you can see we've got like some keywords, in the thousands of keywords that spend $100 or $1,000 a day. Then we've got like, in the hundreds of thousands of keywords that can spend or get 1 click a day, basically. And then there's millions of keywords that get less than 10 clicks a month. But as you can see, it makes up a significant portion of revenue going to different ads or going to different like websites around the internet. So it's important not to ignore this piece as much as you do want to for modeling purposes. So also before we get started, just go through some definitions because I'll probably mention these quite a bit. If you don't understand something, you can just stop me. But so like CPC is cost per click. That's how much we would spend on a click. There's revenue per click, which is you can think about how much revenue you get from a conversion event. So someone like buys a pair of sneakers, that would be a conversion, and that would be how much money that actual conversion is what event is worth. Then there's ad clicks, which is the number of clicks that you pay for. Paid clicks, which think of as number of conversions. CTR1, calling it click-through rate 1, which is your click-through rate on the ad network that you're buying on. So your ad's shown this many times, and then like 1 to 10% of the time you'll actually get a click on it. CTR2 is the number of conversion events that you get on your site over the number of sessions that were driven from an ad click. So just some definitions. So what we're trying to do is, like in most businesses, is maximize how much money you make, right? So these are just two different formulas or math problems of using those metrics to figure out how much money you're actually going to make. So the first one is your impressions on an ad network multiplied by your click-through rate on that ad network, then multiply that by how much money you make for each click times your conversion of CTR2, your conversion rate, and subtract out the cost that you paid for that conversion.
What's an impression?
An impression would be like every time your ad's shown somewhere on the internet. Yeah. And then the other way to look at this is how much revenue you make times the number of clicks you make, or how much revenue per click you make times the number of clicks, and then subtract the number of clicks that you paid for and how much that cost. An intuitive way to think of this problem is the more you bid, the more impressions you're going to get, but you're going to pay more for those clicks that drive traffic. And the lower you bid, you're probably going to be more profitable because you're probably going to make a similar amount for each piece of traffic that comes in, but you might not get very much traffic. Cool. So why have this talk? I didn't want to bore you guys with ad tech data, but I found this kind of interesting. This paper came out in 2016 about using entity embeddings to represent categorical variables. These guys used this to get third place in the Rossman data set in a Calico competition. And since then, it's pretty widely used technique. And I thought this talk was kind of cool because, I was able to apply it to boring ad tech data and maybe make it sort of interesting application in the real world. So starting with a little background, I want to talk about like interpretability versus explainability. So a model's interpretable, you can think of it as like a regression problem where there's an intercept and a slope, and then compare that to a neural network where you have different weights. And if you change a weight, you have literally no idea what's going to happen to the predictive variable. So like to more clearly define that, interpretability is the extent to which you can change the input variables and predict and have a predictable change on the output variable. Explainability, which is kind of an interesting concept, is the ability to explain what's happening inside a model. So I'm using this little picture over here, which if you look at the embeddings, the word embeddings for man, woman, king, and queen, if you subtract the vector man from woman and king from queen, the cosine distance between those two differences is pretty similar. So that's kind of a way to embed the meaning of gender into seemingly random vector of numbers. So as data gets more complex, it's really hard to hold on to interpretability. So sometimes, depending upon your business needs, you can opt to choose for a model that's a little bit more explainable. Cool. So now we've kind of set the problem, realizing we're dealing with super high cardinality categorical variables. And so I want to take a minute to just talk about different techniques for handling categorical variables in general. So to start, they're pretty difficult. I wanted to use like date as an example. So if you have date as a feature and you want to turn this into a tabular data set, like so not a time series, you can create basically an infinite number of features from just that one date feature. Because as you know, categorical variable does need to get turned into either an integer or a float to go into a machine learning model. So there's just some examples like you can use to kind of try to capture seasonality in a tabular data set. So you can do like is month end, day since month end. A cool trick is take like sine day of week or cosine day of week. You can see in that bottom right, I don't know if you can, I can't see that. Oh, sorry if you can't see that. What that's looking like is the kind of sine and cosine pattern. So basically, if you take sine of a number 0 through 6, it'll put like a Sunday near a Monday and a Tuesday near a Wednesday instead of just dummy coding them out so that they're all independent entities. Cool. You can also turn them into other categorical variables if you want, like, and then dummy those out or perform some other technique. So just to go over, so this is like super simple example. One of the most common prevalent techniques is just one-hot encoding or dummy coding. You can take each category within a feature and then create its own feature from that category, and then that cell is just going to be a binary, like it is this feature or it's not this feature. This can blow up the feature space rather quickly, but it's really great for like regression-based problems, so you can attach a slope to the specific category and retain some of its meaning. So especially for like tree-based models, target encoding is a really common technique that's used. What that basically does is it replaces the categorical variable with the mean of the target variable. So this is done on the training set. You maintain a mapper, and then that's going to be applied to the training set or the test set when data actually comes in. So a bunch of techniques to do this to reduce overfitting. You can use a blended average, which can weight based on counts. You can just add random noise, leave one out, or k-fold, where you're using subsections of the actual data to compute the average. And then you can do something like smoothing, so you can set a prior and a posterior as you're calculating these averages. So here's what it looks like. This is just the straight average. If you have high cardinality categorical data like we're talking about in the keyword space, you're going to end up just memorizing the last value, and that's not necessarily what you want to be doing because you'll probably lose a lot of other cool information. So you can do leave one out or k-fold, so you're just basically not including the observation that you're looking at in the actual average. And just to note, this is only done on the training data. This is to prevent overfitting when trying to train either the splits or coefficients that you're placing on these things. I want to take a minute to mention CapBoost encoding, just because I like using this library. They have a cool way of doing it where they reorder the data. So they'll reorder the categories, and then they have this concept of time. So you have a prior, and then as you add in observations, you're going to update the average, and then you're going to shuffle this and do this a few times and average that. So that creates a different value for what this is. Okay, cool. So that was one way of handling categorical variables. Wanted to take a minute to talk about mixed effects models because this was my first approach to this problem, and it worked really well for a while. And it's a good approach to take in general. First thing about it is it's like retains that interpretability, portion that we were talking about. And a mixed effects model is kind of the parent of a linear model. Mixed effects is composed of a fixed effect and a random effect. The fixed effects are pretty much what we're familiar with in terms of just least squares regression. It has a systematic and predictable influence on the data, and you can think of this as like male versus female. But then random effects have non-systematic, unpredictable influences on the data. This is where you're sort of repeatedly sampling a person in a trial, so each person's going to behave differently, but that person may have its own pattern within itself. Cool. So there are a few packages out there I just wanted to mention. I'm mainly familiar with GlimNet and LME4, and then there's some Python packages that work for this. There's a random forest implementation of this, which I haven't used, but I heard is pretty cool. Just wanted to mention those. And then rather than show the actual data, I thought I would just show an example of what this actually does and looks like. So this is from the documentation of the LME4 package. And what this is on your, I don't know if you guys can see this, but so on your x-axis, you have days of sleep deprivation, and then on your y-axis, you have reaction time, and then each one of these plots is an individual. So this individual is repeatedly sampled after depriving them of sleep for a number of days. I'm not sure what their reaction time was to, but something. So there's three different models I'm showing here. So you have your red line, so this is your like complete pooling model, and this is just a regression on the entire data set. So the red line's the same for each one of these individuals. So sometimes it looks good and sometimes it's a bad model, right? Then you have your blue line. The blue line is a subject level. So this is building a regression for every single one of the individuals individually, and you're not sharing any of the information from the whole sample. So I added these last three data points, so 372, 373, and 374, to basically show what this does when you have really odd looking data. So that blue line looks really bad for 372. You would not want to include that in a model. It's probably, and you also only have limited data, so there's only 2 data points there. On 373, there's only 1 data point. So you actually can't build a subject level model from that. You just have 1 estimate. So your green line is your partial pooling. This is where it borrows borrows data or information from the whole sample and uses that to adjust the slope and intercept from the individual. There's a lot of different ways to specify how this works, but as you can see, this is probably the best model for the type of data that we're looking at. And it applied really well to this keyword level model that I originally built. So it has its ups and downs. This worked really great for a while. Works really well on high volume keywords where you have a lot of data on one keyword. You can build a nice regression line. You can specify different distributions, so it doesn't necessarily have to have a linear relationship, and the output looks good. But as the number of keywords grew, as our business grew, and the number of long tail keywords also grew, the model would fail to converge. Not necessarily a problem, but would output a lot of the same sort of naive means, which doesn't look good when it's being manually inspected by individuals. So not the best model in terms of interpretability at this point, nor explainability. Oh, and then so another important differentiation is that the models relied on the fact that a human had to classify all these categories, and these categories were classified to fit a business purpose, not made for a model. So, that actually is probably detrimental to the overall accuracy. Cool. So, enter embeddings. This was the solution to try and solve this problem. So one way to do categorical variables in a neural net, which does work well, is to just one-hot encode everything. But we're dealing with actual keywords here. These keywords do have meaning. They have semantic relationship to each other. And we sort of know heuristically that the outcome variable is grouped by category, and it is grouped by keywords that do mean similar things. But we don't know exactly how or when, nor do we have a mapping of where these keywords should go. So other reasons not to do one-hot encoding is that the the more the higher the sparsity, the more data you're actually going to need to train this model. Computation time increases dramatically, and furthermore, it treats all the words as independent entities, so they don't have relationships to one another. Which is what you're looking for. So there's been a lot of good talks on embeddings today. I don't have a ton of slides on it, so this is just one visualization of how meaning is retained when you transpose these larger vectors to a lower dimensional space. It's what an embedding is essentially, and you can see that like not only are things like male-female relationships maintained, verb tense, country capital, and there's a whole slew of others. So it's like there's a lot of meaning that are in these seemingly random vectors, and hopefully we can use that as a way to help with our predictions. TensorFlow's got a cool visualization. You can just type in a word and it'll show all the other words that are kind of similar to it based on the vector representation that you want. So I just thought I'd show that. It's fun to play around with on projector.tensorflow. Cool. So basically, here was my approach. There's 10 million keywords. We have minimal data on each keyword. What we can start by doing is translate these into each keyword into a 50-dimensional vector. We can use a pre-trained vector because people have pre-trained these things by the location of words next to other words, so we can borrow this. So I did this, I pulled a glove vector, and it only had 40% of the words in the database, which is pretty good, but not enough to actually start this model. People search for, some weird terms sometimes that don't exactly show up in a normal database. So I had to do something else. So here's like a very simple example of how you can use a dummy model to set an embedding layer for keywords that you probably haven't seen before. So we do have a large database of keywords because over time it's grown. So what I did is basically trained a bigram model for every word in our corpus. So a keyword, think of it as like a search query. So there's multiple words in that. So you can just break that into different bigrams, and you're predicting the next word. So it's a dummy model. You train this model, and then you can use those embeddings for each of those keywords and pull those out and hopefully use those in a reasonable way for predicting what you actually care about, which is revenue per click or cost per click, something like that. All right. So this is just like a little bit of sample code. That's pretty blurry, but this is, think just like the PyTorch documentation page, very simple bigram model in training. It's a pretty good documentation there. All right, so did we do anything, right? Like, have we increased either interpretability or explainability? We definitely have not increased interpretability, so hopefully explainability is making sense at this point. So what I did is after training this bigram model, I did dimensionality reduction on the vectors, and then I just sorted by the most extreme values in the vectors to hopefully see if there was some kind of grouping that was naturally occurring. So we can look at the first dimension here, and it looks like some of these words actually belong next to each other. You've got trade schools near me. Well, that one's a little funny. But like cheap motorhomes, used conversion vans. So somehow some meaning's actually getting pulled out here. And then in this other dimension, it looks like we have more like technology communication keywords. And so that's great because there's a ton of different categories in this database. And we've pulled out seemingly 2 categories that probably have some relationship. So just because they might be grouped together semantically now, does that have any effect on the predictive variable that we're looking for? So what I next did, and hopefully this makes sense, let me know if it doesn't, I did dimensionality reduction and then clustered the keywords, and then I plotted a density plot of the dependent variable that we were going to predict. So here I'm just showing CTR2 and then RPC, and you can see that the density distributions just in these 4 clusters is actually becoming quite different. So it looks like we are starting to separate out the words, not just semantically, but also by their behavior in pay-per-click marketplaces. So that's cool. Taking that one step further, I did a regression on the sort of human categoricalization on the dependent variable that we're predicting, and then also did on the same number of clusters from the embeddings that I just made. So if you can kind of see this, the regression is basically showing for the dependent variable that we're looking at, there's really not a significant difference for most of the, so these are campaign IDs. It's like, sorry, that's not the best thing to use, but I thought it would be anonymized. And then, so we're showing that they're not, basically the campaign is not separating the data by the dependent variable. But then you look at the clusters, and we are seeing a lot of significant differences. So the more clusters, the better. We're using 50 dimensions. I think we can sort of begin to come to some conclusion that there is an explainable difference in the actual values that we're trying to predict. So I felt pretty good about continuing on with this model. Great. So this is just sort of like the bookkeeping and actually doing this. So sort of how this worked is that you build this model, then you pull out these weights, and the trick really is just to maintain a mapping of your keyword to the weights that you actually have. You're going to convert the keywords into indexes, and then when you look up the embedding layer, that embedding layer index should match the pre-trained embedding that you just had, and then that feeds into the embedding layer for keywords in your neural network model. One other thing to note is that when you train the model on your first run through the data, you want to make sure you freeze the weights on the embeddings because they're on the keyword embeddings because they're already set to a decent place, whereas the other ones are initialized at random and they will need some training to get to a decent spot. So then you can unfreeze the weights, lower the learning rate, and then retrain, get your final prediction. Cool. And this is just sample code. I just threw this in here because like the model's really simple. Like it's just your sort of standard linear layer model for like a PyTorch neural net. And it's, you have your categorical variables, just looking up the embedding layers. The only one that you're loading in first is your pre-trained one. All the other ones are initialized at random. And then you're going to have some continuous variables as well. And then you're going to predict your outcome. Okay, so let's have a look, see what that actually looks like. Okay, well, here's a slide. We had a few choices. We could have just done general linear models. We used the mixed effects model. It was pretty good. I haven't mentioned GBMs. I have some slides on GBMs. They perform really well, and that was an option. And some of the categorical target encoding techniques would have worked pretty well for some of the really high cardinality variables there. And then we also have neural nets, which were chosen because they helped out with the explainability portion of the model. So can you guys see this okay? That's a little blurry. No. Well, I'll just explain what's going on. Okay, so on your, so each one of these graphs represents, so there's one on the left, this is a keyword, the one on the right, that's also a keyword, so there's two different keywords that we're predicting here. On your x-axis, you have bid, so what I've done is predict the value for the dependent variable, which is on the x-axis, so like we have your paid clicks on the top left, we have your ad clicks on the right there, then revenue per click and cost per click, and then you do that sort of profit equation to get your profit curve, which is right there. So what this is basically showing is if you do a prediction for each bid along this different range of bids, you can start to get patterns that are what you would expect. So most of these graphs you want to go up and to the left. The more you bid, the more you pay. Theoretically, it's the more you're going to make as well. And then so there's a trade-off between how much you pay and then how much you make, and this forms this nice profit curve. The orange dots represent actual data points, so that's what it did historically. So you can see it's pretty messy, so it's really important to be changing bids all the time. The size of the dot represents how far back in the past this was, and I've aggregated this up to the day. So these graphs, look noisy, but this is actually serves to make a pretty good bid prediction for these high volume keywords. So we know we can use this model to set bids for the right position that can accomplish the business goal we make, which is either to maintain a certain amount of volume while understanding how much money we might make or lose for that matter, or just try to find that apex of the profit curve to set the bid to make the highest amount of money. But what's cool about this is that we can also output predictions where we've never seen data for a keyword because of these embedding layers that we have. And we can sort of communicate that these predictions might actually be reasonable because we've shared information already from this embedding layer used in this neural net. And these graphs, they look a little funny, but they're not bad. They're going the right direction. And if you want to start trying out or testing out a new keyword, you can get an idea not only of how much volume it's going to get, of how much it's going to cost, and potentially how much it's going to make based on the bid that you're setting. So I thought that was a cool sort of side effect of building a model like this. Yeah, okay, so start drawing some conclusions here. So GBMs are also a good choice for this. I've used, especially recently, been using gradient boosting with this target encoding technique and one-hot encoding. It's been really successful. If you have super high cardinality, sometimes you do have to get a little more creative and try a solution like this. So one of the downfalls that I've run into with trees is that when you have that many categories, if you're using like H2O, they have this concept of like of the parameter is called enum, and then there's a number of categories that are allowed. So each split of the tree, they're going to reshuffle the categories based on the categories within a feature based on the dependent variable's value. But if you have too many categories, they're going to start getting arbitrarily lumped together. So what ends up happening is that occasionally you'll get a really, really bad prediction, which may give you the best overall, lowest error rate, but someone inspecting the data or looking at a bid may be like, why did you do this? This model might not be trustable. So they also do achieve these state-of-the-art results. And then, using a mixed effects model was also an interesting choice because GBMs don't really have a great way of borrowing from a parent category, especially if you want to specify a parent category. There was the mixed effects random forest package that could do something similar to that. But I was having trouble as time grew on the Glimmer models to converge on these large data sets. Training time went way up. We were using these massive machines to try to train these models on CPUs, so it wasn't scaling as we liked. Another solution, which is interesting, if you want to break your data up into different pieces, is to actually do time series for these high volume keywords. There is seasonality, and to take advantage of that in an explainable way, univariate time series are really great for that. So you could split it up and try that, but the data is way too sparse if you want to have one model trying to predict these keywords. Cool. So some of the conclusions. The choice of model, I thought, should really support what's most important to the business. I think some people have been talking about, how do you define success in a data science project? So you should really start with that and then work backwards to picking your tools and picking what models you're going to use. So that's why we ended up with this embedding solution, which is cool because embeddings actually worked for this. We're not outputting bad, predictions on a daily basis, and buyers are able to look at where your bid is, what you've predicted for each one of the different variables, and inspect, is this a reasonable thing to do? And for the most part, it is reasonable. So you can trust the model, and then you can also show like, oh, it's got the lowest root mean squared error as well compared to the other stuff if you really want to. Then the other thing is interpretability and explainability do have business value. It is nice to be able to show people why you're doing certain things, or it's nice to be able to say, hey, if you change this, this will happen. So you can kind of choose usually one or the other. It's rare you get both. And then, the lowest error rate does not always result in the best results because of compute time, training consistency, and then manual validation. It does need to kind of pass the sniff test, even if your error rate's pretty good. Sometimes predicting 0 on ad clicks is the best prediction because most keywords don't get ad clicks. You really can't predict that. Also, other things to keep in mind is like, if you have a business line that's losing money, every machine learning model is going to tell you just to stop the business line. That's also not an acceptable answer from a machine learning model. So should keep in mind that the metric that your model is optimizing is rarely the lever that it pulls, nor is it the metric your business is going after. So if you think about it, this model, we're trying to minimize root mean squared error. The lever that it's actually pulling is changing a bid. So there's a relative change to a bid. So you can constrain that in a way so you don't harm your business overnight. And then the metric that you're trying to optimize, usually profit, but there's also sort of a minimum volume component too. There's other things businesses will be looking at. So it's important to gather all those requirements first. You can define that sort of math problem of, okay, here are the pieces we're predicting. Here's the math problem. Do we need to constrain this in any way? And then you define your data science problem. Here is the interpretable, explainable solution that I want to use and why. And then you can show your error metrics alongside with those models to show that you've actually made the right selection. In model choice, you've trained it appropriately, and your predictions are not only making sense to humans, but also making sense to machines too. Cool. And I think that's pretty much all I have. I have some appendix slides, but yeah, if you guys have any questions or anything, I could take those now. Yeah.
Yeah, that was really interesting. Can you go back to the slide where you showed the graphs? Yeah, that one. So you said like the more you bid, the more profit. So the line should be going upwards. So right, what's happening in the bottom graph?
Oh yeah, okay. Yeah, it's good to spend more time on this slide. This one's important. Okay, so the bottom slide, and I'm sorry you guys can't see this. Yeah, I should learn how to do this better. So this is your right. This is profit right here. So what that is the math problem of taking your revenue per paid click times your CTR2, then you're subtracting your number of ad clicks minus your CTR1, and you're forming this graph right here. Ideally, or a lot of the times, what this ends up looking like. So the x-axis goes pretty far here, but usually this is going to be U-shaped. So right as you get to, I don't think this goes to 0, but if it did go to 0, then your profit's going to be 0 because you're not going to get any volume whatsoever. If you have a profitable business, odds are as you increase that, you're going to start making money, but not as much because your volume's going to be low. Then there's going to be a threshold, which is sort of your optimal point, and then it's going to start diving because you're now paying more. You're paying more for a click than revenue that you're going to receive for a conversion event. So having it kind of go up and then shoot straight down basically to like infinite loss is, I think, what you should expect from like the profit version of the curve. But the other ones that you're looking at should basically all go up and to the left, at least for these metrics that we're looking at here.
Thank you. This was very interesting. Are you publishing your slides anywhere so we can refer to them?
Oh, yeah, I can. I can post them on LinkedIn or something like that. That's cool. Yeah.
So one of the nice things about using neural nets is that you could potentially jointly train on multiple outcomes. Have you experimented with jointly training against your conversion rates and your revenue?
Oh, that's a good idea. I have not experimented with that. That sounds cool. Yeah.
The question that I had is more related to the metrics. Like, was there any particular reason why you selected those metrics? Why you didn't go with other ones?
Oh yeah, that's a good question. Like, right, because you could just model, you could model profit directly, right? You just be like, how much money am I making? So let's just put this as the dependent variable, build one model, and go from there. And then also there was multiple. There's the other. Where are the equations? I think it's the beginning. There we go. So then there's this other one, impressions CTR1 and CTR2, right? So those are conversion rates, and you can think of that as more of a logistic regression. Did they click or did they not click? Which is interesting. And the reason I chose the second one for this is I have done the first one before too. And conversions are kind of interesting because they can exceed, you can exceed conversion. You can have 2 conversion events on 1 click, which kind of like if you're going for a mixed effects model and you want to specify a certain distribution, you can run into a few constraint problems on using a logistic regression or binomial distribution for your outcome. And it got a little bit messy, and there's some predictions where you'll have conversion events like 10 times conversion. Like think about like Amazon, you're trying to measure, you buy an ad click that goes to Amazon site, and then someone buys 15 different things after that. You want to attribute that back to that first ad click. In terms of a 15,000% conversion rate, it gets a little odd in your data set, but you don't want to throw it out either because it's a super important event. And if you have keywords that are only getting 1 click a month, but their conversion rate could be that high, so think about it, once per year they'll have a 15,000% conversion rate, and then the other 11 months they just go 0 for 1. You don't want to like kill bidding for that necessarily. So that's kind of the only reason. It's just the way the data was behaving kind of influenced the choices that I was making for that. But yeah, you could do a lot of other stuff. Oh, and then the other thing I want to say is I like the explainability of being able to pull it into different pieces. Some of the cool side effects about this is some people only care how much keyword costs to buy, or they only care like on my site, traffic coming in from this category, how much money could it possibly be worth? So the side effects of this model is you can pull out the pieces and then distribute that for other decision making. So sometimes thinking about the side effects are a cool thing to do. Yeah.
Okay, thank you much.
Thanks.